Thank you. So I would like to thank the organizers for inviting me to this very nice conference. So as you can guess from my title, I'm going to talk about maps. And even though we've heard a bit about maps in other talks already, I would like to start with very basic definitions. So a way to define a map is to say that it's a connected graph that's embedded in a surface. So here, most of my talk is going to be on the sphere. So you have different embeddings of the same graph into the sphere, such that, so it's cellular in the sense that the connected components of the complement of the graph are disks, and it's up to isomorphism in the sense that you can deform your graph a little in the surface, but you can't change the cyclic order of the edges around each vertex, because otherwise it's a different map. So this adds a new structure on top of the vertices and the edges of the graph, which are faces. And I'm going to talk about bicolored maps, for which faces are bicolored in black and white, such that every black face is only adjacent to a white face and vice versa. So here, I'm still drawing planar maps, and in this convention, the outer face takes the whole plane, but you can think of it as just sending one point of the sphere to infinity. So it's still, you can still think of it as a map on the sphere. And there are several reasons to be interested in bicolored maps. One of them comes from the Ising model, since you can think of this as a very special case of putting spins, or here black and white, on the faces of your map, with like the proper bicoloration condition can be thought of as the, in a slightly fancy way, the frozen anti-ferromagnetic limit of the Ising model. Frozen because you don't have choices, you don't have freedom once you've fixed the color of one face, and anti-ferromagnetic because adjacent faces want to be of different colors. And a special case of interest, which was what brought me to bicolored maps in the first place, is a case of bicolored triangulations, in particular because they're related to the 2D case of colored tensor models for people in the audience who know about that. And so since we've heard a bit more about matrix model this week, we can relate these maps via a perturbative expansion to a special case of a two-matrix Hermitian model, for which you have only the cross product A times B in the covariance of your measure. And here you can specify the possible degrees of black and white faces by two polynomials, which will appear a bit again later. But I just mentioned this for people who are more comfortable with matrix models, but I'm really not going to use that formulation later. So since we're, well, if you like topological recursion, or for a lot of other reasons, when you have a family of maps, you might want to enumerate maps in your family with boundaries. So distinguished faces that play a special role. And what's very important to follow the rest of my talk is that when you have bicolored maps, you can decide to have boundaries, so distinguished faces, for which you lift the bicoloration condition. So you can think of them as being gray faces, let's say. So I'm still going to, yeah. Yeah.
You allow
Yeah, you have digons. So in this case, yeah, the terms in A squared and B squared, we really interpret them as faces in the map and not in
connection with the same color.
yeah.
Okay.
So, and I'll, if I have time, I will mention that again very quickly in the end. But you can think of it as a different interpretation of having the same color on two adjacent faces. Thank you for your question. So, yeah, contrary to what you've seen, for instance, in Valentin's talk 2 days ago, my distinguished faces are not necessarily in the bicoloration, but okay, you can still think of this case. So here, I'm just taking the example that I had right before. So where now the outer face is really interpreted as a boundary, so a special face. And if you just distinguish faces in a bicolored map, you're going to get the monochromatic boundary condition in the sense that all the edges of the other internal faces that are adjacent to this distinguished face are of the same color, so monochromatic. Then you might have heard of the Dobrushin boundary condition, where now we're out of bicoloration for the outer face, and in this case we have one part of the boundary that is black and another part that is white, and so this is a quite natural boundary condition to use in statistical mechanics if you want to properly define an interface between a black and a white region. And you see that it's still quite close to the monochromatic boundary condition. And one other condition that I'm going to focus on later on is the alternating one, where in this case, the edges that are adjacent to this outer face alternate between black and white. So this is a condition that appears naturally in some random models of bicolored maps, and in particular, going back to the example of bicolor triangulation that I mentioned earlier, it was crucial to get enumeration results about this specific boundary condition to prove that bicolor triangulations converge to the so-called Brownian sphere that I'm not going to talk in detail in this talk, but here is just a very beautiful simulation of this by Jérémie Bouttier. So the Brownian sphere is a random continuum metric space that is very that's universal when you study 2D random geometry. So let me, yeah, and if I have time, I will talk about other wilder boundary conditions, such as this one, where you see that you don't have the alternating condition anymore because you have here two consecutive boundary edges that are of the same color, for instance. So it's related to the Gaussian free field, but it's not the same object because this is a random metric space. and the Gaussian free field as well, a random distribution. But you can, yeah. Oh, sorry. The way this simulation is so okay. So more precisely, if you look really at the details, you can see like small edges here. So it's not actually the Brownian sphere, which is a continuum object, but an approximation of it by a very, very big quadrangulation in that case, I think. So you take a lot of quadrangles and you glue them together, well, randomly with the condition that it makes genus zero surface. And then there are some algorithms to render that in a way that's like, that it's easy to see the, well, you see that it's a fractal object. And so, not really, because it really is a random, you can think of it as a random metric on the two sphere, for instance. So it's like, topologically, it's really just the sphere, but geometrically, it's this fractal object. But yeah, I don't want to confuse you with... yeah. Sorry, I didn't... Yeah. Well, it's... yeah, I mean, this really is not going to be central to my talk. We can definitely discuss that later. Yeah, I would love to talk about it more, but... but like the relation between the two is really not obvious. Well, it's really not really non-trivial to think of it as a random and to construct this as a random metric on the sphere, for instance. Yeah, well, we can discuss that like later if you want. No, it's great to have questions. It's also a topic of interest for me. So, but let's get back to our bicolored maps. So I will recall a few important results on the monochromatic boundary condition. So for that, I will use a bit of notation. So as I said before, I characterize some family of bicolored maps with the possible degrees for the black and the white faces. So Ti and T tilde I. And then I have generating functions of maps in this family with fixed genus G, fixed number of monochromatic boundaries N of respective lengths L1 to Ln. So this depends on T to enumerate vertices and Ti and T tilde I for the faces. And then I pack these generating functions into bigger ones in terms of variables that track these different boundaries. And for the disk, I define a slightly different generating function where I just add, polynomial that characterizes the possible degrees for the black faces. And so there are well-known results by Eynard, Valentin, and Chekhov, who proved that this family of generating functions satisfy topological recursion, and that there is an explicit rational parameterization for the disk, which depends on some functions gamma, alpha k, and beta k that depend on the possible phase degrees, and that I'm not going to write out explicitly. So, as you all know by now, the fact that this parameterization is rational is equivalent to the fact that the associated curve has gene 0, which is a typical behavior in map enumeration problems. So if there are no questions about these results, let me get on to the alternating condition. So the nicest things that we've proven with Jérémie Bouttier are on M constellations. So you've seen that already in Valentin's talk. So in this case, the possible phase degrees are just M for the black faces and multiples of M for the white faces. And once again, I have some first sequence of generating functions. So here I'm just on the disk. So I'm gen 0 with one boundary, and I have these generating series AR when the length of the boundary is fixed to be equal to 2R. And yeah, you can notice that to have an alternating boundary, it has to be of even length necessarily, which is why I divide it by 2. And then I pack it into a bigger generating series with omega, that's the variable corresponding to the boundary length. And we proved with Jérémie Bouttier that this generating function for the disk also has an explicit rational parameterization, where here I define explicitly the alpha k's and v, which are auxiliary functions that were also appearing in the previous, in the parameterization for the monochromatic condition. And more explicitly, as I will explain later on, actually the alternating, or the curve for the alternating case is really closely related to the one for the monochromatic case with these explicit expressions. So you see that I didn't use the same variable for the parameterization for the alternating and the monochromatic case, because the natural variable for the alternating case is here S, that's Z to the M, where Z is the variable for the monochromatic case. So in a slightly fancy way, you can say that they're related by a branched covering. And one thing that's very nice in this relation is that the behavior of the symplectic structure through this covering is the simplest thing that you could hope for in the covering of degree M, because here, so if you take the pullback of the symplectic form associated to WA through this covering, you just get the symplectic form, associated to X and Y multiplied by this integer M. So if you hope to have a sort of conservation of volume when you go through covering of degree M, that's really the nicest thing that you could have. So as we've heard a lot this week about the symplectic invariance of TR, it would be interesting to see if there's a relation with such results and constructions. And so yeah, this contributes to the new structures part of my title, and just an aside for the universal behavior part. So what my initial motivation to get these results was actually something much weaker, which are asymptotics for the enumeration coefficients, and you can get them from rational parametrizations through singularity analysis. And when you do that, you get really the same behavior as for any nice family of maps on the disk that you can think of. So, well, yeah. Yeah.
Exactly M.
Exactly M. Yeah.
And the other one has.
Yeah.
But from the
Yeah.
for any.
Yeah.
You don't.
I will talk about it. Yeah. So you will. I'm right now going to talk a bit about some parts of our proof, and you will see where things get difficult for general phase degrees. So you're anticipating the next slide. The idea for a proof. So yeah, the first part of our proof works for any phase degrees. So as is the case for usually for map enumeration problems, you want to get a Tet recurrence equation. So if you try to, yeah, here with this gray arrow, I'm showing the edge of the boundary where I will start exploring the map. So I will basically remove the internal face that lies on the other side of this edge. And if you do that just for starting with just the alternating boundary condition, it's not stable because just after one step, you lose the alternating property. So you have to look at a more general boundary condition. And it's actually one that mixes the monochromatic condition that's well known and the alternating one that's the one that we're interested in. So I'm going to make a lot of, to show you a lot of drawings that look like that. So just so it's clear for everyone, when I draw a big circle with like little black trimmings on it, it means that inside I have a bicolored map where when there's a black bit inside, the adjacent face is white, and when there's no black thing, the adjacent face inside is black. So I'm taking maps with this mixed boundary condition. So I'm using a bit of additional notation for this more general mixed condition with the functions M. That makes so A, I'm just reminding you from a few slides ago, that enumerates the alternating condition, and W that enumerates the monochromatic one. And so if we look at the different possibilities of what lies on the other side of this boundary edge, basically either you have a proper internal face, which will add some factor Ti correspond where I is the length of this face, or it can be identified with another edge on the boundary, either one in the monochromatic part or one in the alternating part. And so in these two cases, what you get after seeing that this edge is identified with another boundary one is like two submaps. Either you have one with a monochromatic condition and one with a mixed condition, or you have one with a mixed condition and one with the alternating one. So if we pack that up into our bigger generating function, you get this set equation for this more general boundary condition represented by M. And one thing that's very nice about this equation is that it's a polynomial of degree 1 in M. So this means that you can apply the so-called kernel method to it. So in other words, you reorganize your terms to have some function k that doesn't depend on M multiplied by M equal to some function R that also doesn't depend on M. And so the kernel k is really simple in all cases, but the remainder R, in full generality, it's a bit complicated because it contains these initial terms of M. So where here x to the x to the larger or equal to 0 means that I take the coefficients of this function, this generating series in X that have non-negative coefficients. The idea of the kernel method, or this variant of the kernel method that we applied, is that if we find some function omega of X that for which the kernel vanishes, then necessarily from the way we wrote our equation, R vanishes as well. And so we would have two equations for our two unknowns, omega of X and A of omega of X. So as I've just said, if you stay in full generality, these extra terms here in R are kind of hard to deal with this version of the kernel method. So you don't get a nice explicit expression, but you still have general theorems that tell you that M, and so in particular A, are algebraic in all these variables. So let me get to a special case of constellations, where here, so just a slight simplification of notation first. So since, we can have a few, fewer variables for the white faces, and for the black faces, actually, since they're all of degree M, this variable is redundant with the vertex variable and the ones for the white faces, so we just set it to 1. And so one very important observation is that the monochromatic part of the boundary has necessarily to be a multiple of M. So this annoying function R gets much simpler because this part is just a monomial, because the only term here that has non-negative, that is a non-negative power of X is this one. So in that case, from what I've just explained about the kernel method, you get these two equations on omega and A, which are the ones that I wrote already right before. And then, since we have already a well-known nice parameterization of X and Y, we would just plug it into that. So if you don't have questions about that part, I will put things into a bit more of context, because here, so we've established a direct relation between the monochromatic and the alternating conditions, but there's actually sort of in some sense, a very long path that you could take from one to the other, because so in the work of Eynard and Valentin, they didn't only get results for the monochromatic or the Dobrushin condition, but they also looked at fixed numbers of monochromatic parts along boundaries. So the way they describe it is by giving two permutation profiles for the way the colors are organized. So the idea is that you fix sorry, thank you. So you fix some integer k, and it's going to be the number of color changes that you do along your different boundaries. So, for instance, if you take k equal to 3, you could have two different boundaries, and you know that you want to have well, 3 white parts and 3 black parts distributed along your 2 boundaries. So one thing that you could have is something like that, because in total you have 3 black parts and 3 white parts along your boundary. So you can encode all. I don't think I will use a blackboard apart from just this, so thank you. So you can encode the different ways of distributing 2k monochromatic parts of a boundary by 2 permutations. And so once again, you can pack that into a big generating function. And more explicit results that they've obtained is for the non-connected version of this big generating function that you can interpret as a matrix on permutations. And there's a characterization of the eigenvectors of H, so this big matrix in Eynard's book from 2017. And in the case of the disk, they have a more explicit relations with coefficients related to planar link patterns. And why am I talking about that in relation to the alternating boundary condition? It's because, so here you see you're fixing the number of color changes that you have along your boundaries. And for the alternating boundaries, you change your color for every edge of your boundary. So it's kind of the limit of this of this construction. So since it's the limit of it, it's not in the scope of these results where the number of color changes are fixed and you let, for instance, the size of a boundary go to infinity. So as I was saying, our result on the alternating boundary condition, and in particular its relation with the monochromatic boundary, give a sort of relation between the starting point and the limit at infinity of this recurrence. And other boundary conditions that are interest in random models of maps are kind of a step in the other direction, going from the alternating condition to the monochromatic one. So in particular, this mixed alternating condition, where now the configuration of colors along the boundary are given by words on the alphabet, black, white, and black, black, white, white. So here, in this particular example, you see that you have black, black, white, white for the edges along the boundary, then black, white, black, white. So it's an example of that. And so here we're starting from the alternating condition and increasing the number of consecutive edges that are of the same color. So that's why I'm saying it's a step in the other direction. And to wrap things up, I wanted to just mention my current projects extending what I've just said. So with Valentin, Baillard, and Bertrand, Eynard, we're currently working on precisely what Alex asked about. So getting a nice expression for the alternating condition on the disk for more general phase degrees, and then hopefully getting the whole topological recursion going on to higher general and number of boundaries, and comparing it to what we have for the monochromatic condition to investigate this sort of symplectic covariance, maybe, that we have for the disk. And on the other side, I'm working on my own with for this mixed alternating condition that I just mentioned, because it has some natural applications when you look at bicolored quadrangulations this time. And just to talk about much longer term things. So I started by saying that this is that bicolored maps are the frozen anti-ferromagnetic limit of the Ising model. But as we've discussed about the roles of the digons in this model, if you take digons and then you don't really care about the number of digons that you have, but you just contract them into edges when you have a sequence of them, then you can think of these digons as representing the coupling constants of your Ising model, because you would for other faces you will either have different colors of or the same depending on the parity of the number of digons that you have in between. And just to also connect with what Valentin talked about a few days ago, since we also have these underlying, these auxiliary functions alpha k that are related to mobiles, we would really like to be able to have a bijective proof of our formulae, hopefully with slices, but it's currently out of reach for, in particular, the alternating condition. So it's a much longer term goal. So let me stop here. Thank you for your attention.